Hi everyone, I'm Arnaud De Coster, researcher at the VUB in Brussels, and I will present a design method for modular shell structures in textile reinforced concrete to complete a geometrical as well as structural study. Before starting, I would like to thank the organizing team of the conference to make everything possible virtually. So a big thank you for this. Shell structures have always been of a major interest to architects and engineers. The optimal force flow within their structural layout enables to achieve impressive spans over single uninterrupted spaces. With a dominant membrane stress state as a result, the building material is most efficiently used, and thin sections can be obtained. Unfortunately, concrete shell structures are associated with some drawbacks. These are neither linked to their design nor to their optimization, but related to more practical reasons, their fabrication. A decrease in the use of shell structures was noticed during the last decades. And the aim here is to recover their initial value in industry as structural efficient shapes. The study presented in this paper is twofold. The first part consists in defining a modular shell element and afterwards studying its capacity for combination towards multiple configurations. The geometry of the module is obtained by parametrization with the help of Rhinoceros and Grasshopper software. In here, the boundary and the load conditions can be easily adapted to modify the overall shape. Subsequently, these shell shapes must suit into a larger number of configurations and still need to be valuable as shells. The methodology is established on the form finding of an equilateral triangular shape with three identical arched sides. The form finding of this equilateral triangle started with the parametrization of a flat surface in the XY plane. Three identical arches having the same curvature, the same length, and the same height were defined. During form finding, all side particles were attracted to these arches, all acting as supports of the resulting synclastic shape. After the form finding, further modularization was possible. The shape is a periodic shape, which means that beside their potential of creating a continuous uniform pattern with solely themselves, they are rotational symmetrical. Identical to their ground plane, they have a threefold symmetry, resulting into three planes of symmetry. When these plates are considered section planes, 6 parts are being created. In there, we recognize 3 pairs of modules. So 1 repeating pair in the configuration. With that pair of modules, different configurations can be made, as you can see on this slide. And then by organizing them in a kind of tessellation grid and by removing subsequently some modules, different configurations can be achieved, as you can see. To avoid some unrepresentative stress concentrations at the supports, 1 triangular element was removed at each ground connection to achieve a larger base of 45 centimeters. After identifying the surface as a monolithic conventional shell in the finite element software Abacus, additional parameters were implemented for the analysis, such as the material properties and the gravity load. To verify the efficiency of a given combination of modules, an analysis under self-weight is done in terms of internal forces, stresses, and displacements. This study started with the numerical analysis of the form-found shell, and in the second part, 3 different configurations have been selected. So for the synclastic shape, as the schemes show, the middle part of the boundaries and the parts of the structures just above the ground connections, called pillars, are the weakest zones due to bending occurring there. The first one is seen with the presence of some tensional stresses related to the fixed edges during form finding. The first configuration, with the addition of cantilevered edges, largely improved the structure, not only in terms of maximum stress values, but also because the general stress state is more uniform, in which both displacements as well as bending moments are reduced. The pillars too are highly improved with the additional stiffness provided by the new layout of the modules. Analyzing the second one, the umbrella shape, we can directly understand its behavior being influenced by the cantilevered part of the shape with a lack of stiffness at the outermost corners. Therefore, this shape, even though its aesthetical interest, is less efficient as a shell structure. Finally, the 6 additional outlying ground connections provided by the last configuration led to a considerable reduction of the maximum displacements as well as the bending moments. This can be explained with the redirection of the external forces in 2 directions. Under pure self-weight, different designs and their respective efficiency have been inspected. The general conclusion, which resulted from this analysis, is that some shell configurations emerging from the combination of the form-found modules, rather than the basic form-found triangle, do display an equivalent and sometimes even improved load-bearing behavior under self-weight. Even if their general shape has not been globally optimized, they do not necessarily demonstrate a lower efficiency. Subsequently, combining modules first for manufacturing and economic reasons is not necessarily at the expense of the structural efficiency, and the modular method can be confirmed. Thank you for listening.